should be written like this.
I did the exact same thing as Alan, but then when you get 99% for your lower tail test.
So here's the thing.
What
I think this happened last year, if my memory strikes me correctly. So, and then I advise the students to do it this way, because this way, to me, is more proper. Because if not, the logic is that we're setting up an alternative hypothesis that is greater than 15 minutes, which is not the claim we're trying to make. And so what happens there, if you do the greater than, we end up, the company's objective, the company wants to know if this can be done in 15 minutes or less.
They want to know H of O, and what you just wrote down.
Which, if that's kind of their goal of what they think is happening, or what they want to know is happening, then the only way they can get it is through a fail or reject hypothesis, like a test that isn't conclusive.
And this wouldn't be that.
Yeah.
This is conclusive.
I would say, either way, and this happened last year, where there was a difference between me and Daryl on what you guys should do.
Who won? Who won?
I think both of us won. I think
Maybe if you write an argument of why what you chose.
Yeah, I mean, I would just either way. I would I would explain yourself in your answer. I would say, hey, logically, if the company is trying to prove that less than 15 minutes is what they think, they want to know if this can be done in less than 15 minutes, then this would be the alternative hypothesis they would use.
It does, I mean, the question says less than or equal to.
Mine's on that stuff.
We can't prove less than or equal to. Right. I mean, that's what I would argue.
Which is why I remember.
Which is why you have to go this way. Yeah. And this is kind of like, I'm really too into the weeds on this for this class, but you can prove less than. But the less than or equal to, the only way that is successful within a test is if it's a test that is inconclusive. Because if you fail to reject the null, you essentially have a test that is inconclusive. You do not prove something. You fail to disprove something.
So the second part of that would be if you do write it.
I would say write it either way.
If you do write it the Matt way, does it change anything?
No. If you write it the Matt way, and this is what your hypothesis tested, and this is your sample mean, and that's your stated value, then this is clearly going to be a fail to reject the null, because your sample mean already came in 2 points above your stated value, and so if we think about if this is our stated value on a distribution, we have distribution here, and stated value is 15. And we did a lower tail test. So we're saying this is the area we want to focus on. Our sample mean came in at 17. So we know right away that this is going to be a fail to reject test. Accepted, yeah. Okay. So in my world, logically, to me, I would set it up this way. I think last time some people said it this way, some people said it that way. I would explain yourself either way you do it. I think you'll probably give everyone credit.
If we set it up the Matt way, it's accept. If we set it up the other way, it's reject.
Yeah, what does your p-value come back to? Like 99?
Yeah.
Yeah. So yeah, it's going to be, you're either going to fail to reject if you set it my way, or you're going to reject the null if you set it up your way.
Isn't it impossible if you set it the other way to accept because the average is higher than 15? There's like absolutely no way to.
No, yeah. If you set it the way I think you should set it up, you're never going to reject it.
Right.
But I don't know, the way the question is worded, I would argue my way is probably, but. One circle. This one's mine. This is what I say. This is how I would say to set it up. You guys can do either way. Just explain it out. your logic behind it. As long as you explain your logic behind it, I'm sure.
I mean, what's the worst that can happen? We can get an F. I mean, geez.
I'll email him.
It's not that big a deal.
I'll email him
Yeah.
again because, I mean, we had this debate last year between me and him.
It is it.
Where, and you guys just bring up that we did an example similar to it, and then I said to do it the way I said to do it, if he does mark you off, or you can just do it the other way, and I don't know which one to mark you off for. But just put a written explanation in there, and then I'll email him tonight and say, hey, we had this came up again like it did last year. The same test.
On the last, assignment that we have, there was a problem where, with the timing and
The timing one, yeah.
the timing one, yeah, there's, and you said the same thing, that's where there's the same issue. It doesn't matter. Take out.
So yeah, my argument would be, I mean, who cares about my argument? For your guys' sake, either one can work probably if you write out an explanation. But there's an inherent like mistake in setting up a hypothesis test the way that makes sense with the p-value. Just because you're trying to make a claim of can this be done in less than a certain amount of time.
Golfing? That's more important.
You helped him way too much, Chelsea. Well, it's homework. It's all done. It's golfing.
He always wants to golf like Thursdays in the afternoon though. Oh,
Yeah.
I did work. Oh, yeah.
Yeah.
Okay, so for that one, I'll email him. I'll cover your bases on that one. I'm sure we'll all be fine.
So with your way, you put the higher p-value.
Yeah, you'd have the higher p-value. P-value would be super, super high. I'll email him about it. I would argue that the way the question is written, to put a structurally valid test with a result, the result we're aiming for is less than 15 minutes. And the only way I would know to set that test is make that the alternative. But I'll email them and then we'll solve that out. So don't worry too much about that. Just kind of write out a reasonable explanation for either one, and you can go with either one on that. I believe the original correct answer last year was not my way. And then I believe I discussed with him my way. And then I think he just gave everyone credit, but I think he was swayed to my side of the story. I'm not certain. I may be wrong.
Half of it's
No.
We've already colluded enough on this question.
So a lot of collision in this question. Okay, any other generic type questions on this?
Specifically generic?
Yeah.
Are we good with the midterm?
Is it possible if it's not too disturbing for everybody who probably are ahead of me? Pivot tables, can you review quickly, kind of like stock on tab B for the midterm? So is it possible that the refresh had to set up the information in a way that we follow what he's asking? Does it make sense what I say?
How do you do a pivot table like that? Okay.
So, kind of the best, so we have to select all the data to start to the table. We insert pivot table. We can tell it where we want the output at. Hit OK, and then we start a pivot table there. So he's going to ask you to do a couple things. First thing he asks you to do is a frequency distribution. So we're looking at different companies, what stock exchange they're on, what's their ticker symbol. So let's just look at different exchanges. So we have 3 major exchanges. And let's look at how many companies are in each exchange. So here we have a frequency table. So there's 3 different stock exchanges. The first stock exchange has 5 companies on it. The second stock exchange has 3 companies on it. And the last stock exchange has 17 companies on it. So that's just our frequency distribution. He might ask us to do a relative frequency distribution. In order to do that, we just go here to value field settings. And then we do show value as % of grand total. So now, instead of showing just counts, we show % shares. So this one, instead of having whatever it was, 5 companies, this one, 20% of the companies are in Amex, 12% are in New York Stock Exchange, and then 68% are in OTC. So that's probably the simplest ones we do. From there, we can do what's called a cross tabulation. This one's going to be hard, the cross tabulation. Let's go find it different. Let's do this. Let's take our market cap. We're going to see that our market cap begins at 23, ends at 295. So we're going to group this. We're going to group this together. We'll go from 25 to 300, and we'll go by intervals of 25. Company in here, and then instead of percentage, we're just going to show them as no calculation. So now we have a cross tabulation. Now we're looking by size of market cap, so how much the company is worth. What is the distribution of companies within each stock exchange? So we can see here that Amex has mostly small market cap companies. New York Stock Exchange has medium market cap companies, and then our OTC has a wide spread all over market cap sizes. So going back to, we want to go back, if he wants us to make a histogram, we go options, and then we can go pivot chart. Let's click on a nice bar graph. And so now we have a histogram. If he wants us to do a pie chart, we can go back to a relative frequency distribution. Just present a grand total, and we show our values. And we can say pie chart. And then we go pie chart. Other questions on those? Or? Looks like you're asked to do frequency and histogram, and then a cross tabulation with 2 variables. So with a grouping. So remember, when we're doing that cross tabulation with the grouping, we got to see what our minimum point is. We got to see what our maximum point is. And then we got to group between those. So here we could group between 0 and 300 by groups of 50. And that's how we get our tabulation between the two variables. Okay, other midterm questions? Remember in the midterm review I sent you guys, the easiest thing and the most helpful thing out of that is your question will specify whether you have a population standard deviation or a sample standard deviation. You have one or the other, you don't have both. If you're given a population standard deviation, there's templates for that. That's when that little squiggly guy is known. So if the population standard deviation is known, then you use population standard deviation, or you have templates that came with your book and the data sets. If it's not known, we use a different template. And the main difference between these two templates is instead of calculating a z-test or a z-distribution, we're now doing a t-test or a t-distribution. And for our midterm, the big difference there is we have to calculate this degrees of freedom. Because our t-distribution changes based on our given degrees of freedom.
I'm not going to do it. I'll go anywhere.
So let's start doing some homework. Yes. Exciting stuff. First question says, the data that follows reports the average annual costs for attending a college for a sample of private and public colleges. So what we're doing here, we have private colleges, we have public colleges. We want to see which one costs more. So what is the mean cost for private colleges? That's just going to be pretty easy. We're just going to go the average. The mean of what it costs to go to a private school costs $42,000 on average, $42,500 on average to go to a private school. What is the sample, what is standard deviation in the sample costs for public colleges? So this one's pretty easy. You go in here, we can say standard deviation of a sample for public colleges. We have 5.32. So what is the point estimate difference between, is the point estimate of difference between the sample mean significant and alpha value of 0.05? So what this is asking us to do is set up a null hypothesis and then run a test on whether or not these two mean are different from each other. So the point estimate difference, what we're saying is our null hypothesis or alternative hypothesis is on the cost of private colleges equal to the cost of public colleges, or is the cost of private colleges not equal to the cost of public colleges? So we are not given a population standard deviation here. So we can go to data analysis. If we're not given a population standard deviation, which we aren't here, are we using a z-test or a t-test? t-test. So t-test, we're going to assume unequal variances. For this class, we're always going to assume unequal variances unless we have a paired test, which we'll run into later. And this is clearly not a paired test. There's more public schools than there are private schools. So we're going to do a t-test for 2 samples, assuming unequal variances. So they did not specify a hypothesized mean difference. So our hypothesized mean difference here is going to be 0. We included labels in the first row, and our alpha value is going to be 0.05. Our output range, we'll just pop it right here. So what is this output for us? It tells us the means of each private and public institutions. A mean of private institution tells us 42.5, which is the same as what we just calculated. It tells us the variance for both public and private institutions. And as we know, the variance is just a standard deviation squared. So we take the square roots of the variance for public schools. Should be pretty close to what we have, and it is. So boom, we're good. It gives us a t-statistic. This is our calculated t-statistic. This is the difference between these two divided by their shared variance, which it doesn't have calculated for us, but it gives us a t-statistic. And then it gives us one-tailed test, two-tailed test, critical values, and p-values. So there's 2 ways we can run these tests. We can do a critical value test or we can do a p-value test. It's much easier to run a p-value test than a critical value test, because a p-value test, you just compare what the p-value is against whatever the stated alpha value is. So the stated alpha value for this one was 0.05. So remember, this is a two-tailed test. So for a two-tailed test, we look at this p-value. The p-value is really, really 0. So if it's really, really 0, it's going to be less than an alpha value of 0.05, and we're going to reject the null. If we'd rather do a t-value test, then we look at our test statistic, take the absolute value of that, and compare it to our critical value. Take the absolute value of that. We want, in order to reject the null, value of our t statistic has to be greater than the absolute value of t critical. So for this one, 7.87 is going to be greater than 2.13, so you reject the null, we both come out with the same conclusion. So is the point estimate difference between the sample means significant? Yes, it is significant. Our p-value is 0. So with p-value 0, we reject the null that the 2 means are equal. And so if we reject the null, the 2 means are equal, that means they are statistically different than one another. And that's basically all we need to know for this question. Yes. Did I answer the question? Or?
Oh, no, I
I thought you raised your hand. So there's 2 ways to solve this. This is the quick way. The quick way is by going into data and doing an actual t-test within data. We actually have a
This is what you sent to us today.
Yep. So in this one, we do not know the standard deviations of the 2 populations. So no. Please. So we can either use the template or we can use the calculation. When you're looking at your template, all you really have to do is make sure these are referencing the proper data sets. We can change this from Cherry Grove. This is going to be private. Beechwood, this is going to be public. I'm going to output all this information for you. Then we can look at our test statistic, which is going to be the same as our test statistic we're given here. And our p-value, which is going to be the same as our p-value that is given here. And so once you properly fill in these 6 values for this test, the rest of your test is going to run for itself. Questions on this template versus doing the test in data? It's much, yep.
Which one did you say was the p-value? Is that the one for, let me see, the above the T critical 1 tail? Or,
The p-value for 2 tail. Right here.
oh, okay. Because for that one, I got 1.75.
No, 1.75 is your critical value.
Oh, sorry, okay,
The T critical 1 tail,
it's below.
it's the one that says P 2 tail on it. That's your p-value for 2 tail test. Okay, questions on this one? Allows tab B. What was your tab A? Let's go back to tab A then. Let's solve tab A first. So, this one says, essentially, researcher had a satisfaction survey between 2 stores, Kmart and Dollar General. And she is trying to determine if customers of these stores are similarly satisfied with their shopping experiences. So similarly satisfied with their shopping experiences lets us know that we're going to be running a 2-tail test. So there's a few ways we can write this out. We can use a mu or an x, or we can notate s as the score, but we go with x. We say x of Kmart is equal to x of Dollar General, or our value for Kmart less our value for Dollar General is equal to 0. Logically, these are both the same statement. So either one is equal to the other, or the difference between the 2 is equal to 0. So either way is proper. He'll probably be good with either. He'll be good with either way. I'm good with either way. Our alternative hypothesis then would be or so we're trying to test whether or not these 2 means are different. It says here on the third part, assume that the standard deviation is equal to 12 for satisfaction scores at both retailers. So if we're assuming the standard deviation is equal to 12, we're assuming that's the population standard deviation to be given to us. And so if we know the population standard deviation, we can go to this template, an interval estimate for the difference in population means when the standard deviations of both are known. We copy this template over. So in this template, everything that's highlighted yellow are numbers that we have to input. So with these questions, we can either be given pre-calculated values or we can be given data sets with which we have to calculate our values. This question has given us pre-calculated values and no data. We're given sample size and the average satisfaction score. So we can copy these over to here. But we're also given a population standard deviation. So this we have to also input what our population standard deviation is here. We're assuming that it's 12 for both populations. As you see, when you type in 12 and change it up, it's going to change all of your answers throughout here and calculate it for you. So what we're saying is Kmart stores on average customers on average have a 79 score in their customer satisfaction. Dollar General stores on average have a 71 score on the general satisfaction. We want to look at this with a level significance of 0.05 as our alpha. So our critical value we're going to be comparing is 1.96. But we don't have to worry about that if we're just doing a p-value test. And our p-value test for this hypothesis test we set up, our p-value is going to be 0.0138. So for p-value is 0.0138 and our critical or our alpha value is 0.05, 0.0138 is less than 0.05. So we're going to reject this null hypothesis. So we reject the null.
You say the whole gotta go? Would you say the whole gotta go?
That was Amber.
Oh, it's Amber?
So our conclusion, if we reject the null, is that Kmart and Dollar General customers do not have the same satisfaction scores. And that's their scores are statistically different. The difference in their scores is statistically significant.
Sure. A quick question on the template that you copied over. There was a z-test for 2 sample means. We can only do that if we have all the data, right?
Yep, we can only do that. So if this came with data, you're right. With data and they're reported to us what the population standard deviation was, but it also came with data, there is a z-test for 2 sample means. We would use that within the data function.
And it would be 2.
It's going to be a 2-tailed test, yeah. So the other part of this question is ask us for a lower limit of the confidence interval for the point estimate difference between these means and the upper limit. So what they're saying is an alpha value of 5 or 95% confidence. Tell us what we know the lower limit will be and the upper limit will be, and the difference between these two means. So this is already calculated for us. Our lower limit is 1.63 and our upper limit is 14.37. So with 95% confidence, we know that the difference between these two means is going to fall somewhere between 1.63 and 14.37. And that's important to us because between 1.63 and 14.37 is not 0. So we're 95% confidence that the difference between these two means will not be 0. Thus, we can say that with statistical significance at 95%, these two means are not equal to one another. Questions on that one? Very good. Tab B. Tab C. Consider the results for reported math and writing scores of a sample of 12 students. So this is going to be a little bit different than one we did before. 12 students, we're having to take 2 tests. We're taking a math test and a writing test. We're going to get 2 scores. So that gives us a paired sample. So paired samples will only occur in situations like this, where we have 2 students giving out 2 scores, 2 outputs, one student giving us out 2 scores, one computer giving out 2 outputs, one machine taking 2 different sets of time to do a job. Whenever it's one person or one individual giving out multiple scores, we're going to call that a paired sample. So the first, our hypothesis test, are there differences between math scores and writing scores for the sample significant at a 5% alpha value? So, two-tailed test here. The score for math, the score for writing. Again, we can just say whatever notation we want to use here. And then our alternative hypothesis. Is that they're not equal. So, sample, we can go to data analysis. We're doing a t-test, paired two sample for means.
You know, it's paired just because it's the same number in each.
Yep, and it's because it's one single entity is outputting two things. So it could be something like this: is one single kid is taking two tests. We can run, say, a lawn care company, and we have a push lawnmower and a gas-powered lawnmower, and we can have all of our workers mow the same lawn with a push mower, then mow the same lawn with a gas mower, and see if their times are different, stuff like that. As long as it's one single individual entity is producing two outputs, and it's all matched up throughout, that's when we're going to do a paired test. The key is on paired tests, we're usually going to have 3 columns of data. Because you'll have the 2 outputs, and then you'll have the column that denotes some sort of identifier for the person or the machine or whatever it is. Range 2, we included labels. Our hypothesized mean difference is 0. Alpha value is 0.5. We're going to put this right here. So, our mean math score is 514. Our mean writing score is 489. Gives us our variances, gives us our counts of observations. What we're most concerned with, though, is this is what our t statistic is, this is our t critical value, and this is our p value. Our alpha value is 0.05. If our alpha value is 0.05 and our p value is 0.039, 0.039 is less than our alpha value. So if our p value is less than our alpha value, we're going to reject the null hypothesis. So if we reject the null hypothesis, we're saying that for this sample of students, there is a statistically significant difference between their math score and their writing score. There's a difference between the two, and that difference is statistically significant. And then by logic, we can look at the 2 means. Math mean is higher than writing mean. If we know they're statistically different, and we see that the mean, one mean is higher, we know by logic that they have higher math scores than they have writing scores. And the point estimate difference between these 2 means is just that, just the space between the 2 means. The point estimate difference between the 2 means is 25. Questions? We good?
Why did I spend 15 minutes trying to find out last answer?
Which one? The 25 one? 25 one is one that's almost too simple. You should know it couldn't be that. That's, yeah, whenever we say point estimate, that just means difference between 2 things. Or if we want to know the point estimate for proportion, that's literally just the proportion for a given population. So, D sets. 4 different paints are advertised as having the same drying time. To check the manufacturer's claim, 5 samples were tested for each of the paints. The time in minutes until the paint was dry enough for a second coat. So now we're not testing the difference between two samples or two populations. Now we're testing multiple samples. So the first thing we have to do is write our hypothesis test. Or x1 is equal to x2 is equal to x3 is equal to x4. We're saying that the drying time for 1 is equal to the drying time for 2 is equal to the drying time for 3 is equal to the drying time for 4. So as long as one of these does not hold, then our alternative hypothesis is that H0 does not hold. So it's a little bit different of a test. It's a test that it's easier to reject the null on a test like this, because instead of saying, are these two populations the same, we're saying, are these 4 populations all exactly the same? So populations 1 through 3 are the same, but 4 is different. This test, we're going to reject the null. So this is a test where it's kind of easier to get the outcome we want to know if there truly is a difference. Which paint had the fastest drying time? We can answer that question in a second, but to do this, we're going to go to data analysis. ANOVA, we're only working on one single factor. We're going to highlight this range of all of our data. There's labels in the front row. First row, our data is grouped by columns. Alpha value is 0.05, I believe. We can say an output area. We want it to be right here. Hit OK. So to give us out, it's going to give us 2 printouts. The first printout is just going to give us all of our summary statistics. What's our count in each one? There's 5 in each of our 4 samples. What's the average in each of our samples? What's the variance in each of our samples? So the first question says, which paint had the fastest drying time? The paint with the fastest drying time is the paint with the lowest average drying time, paint number 1. So if we looked at strictly at averages, we would say that paint 1 had the fastest drying time. But it's probably not a good idea to take a sample of 5 and make a declarative statement. So we run this test to see, given the variance of these drying times, are these groups statistically the same or are they different? The number we're going to focus on this table is our p-value. Our alpha value is 0.05, our p-value is 0.09. Bless you. We're going to fail to reject the null. So if we fail to reject the null, then statistically, the drying times are not significant at a value at an alpha of 0.05. So statistically, we can't prove that these drying times are different from one another. So here comes the next fun part. Assume that the sum of squares within groups remains the same.
And I'm sorry, did you say that, so the drying times are actually, they are different from one another?
They are not
They're
different.
not.
They're not statistically different from one another.
So then, when you accept it, because it's equal to across the board on the null?
We failed to reject.
Yeah, you accept.
Oh. So-
I'm sorry, I said fail to. I gotta see this to
sorry.
that. You accept the null hypothesis.
Got it, okay.
So except because there's no difference, therefore they're the same.
We're saying that the difference is not enough to be statistically significant. So since we took such a small sample and the variances are so widely varying between each sample, we're saying that we don't have enough information to prove that they're different given this sample. So last part says, assume that the sum of squares within groups remains the same. What is the minimum sum of squares between groups where the analysis would result in a significant difference in drying time? So on page 577, we're going to look at some formulas. we have sum of squares, right, our degrees of freedom, we have our mean squares, we have our F, and then we have our F critical.
Can you say that again?
577. So we're saying that our within groups, we got between, we got within. If our within groups values remain the same, 692, degrees of freedom 16, our mean squared is 43.25. Our degrees of freedom here will remain the same at 3. But if our sum of squares changes, that means our sum of squares changes, that means our mean squares change, and our F value changes. So they're asking us is what value for the sum of squares between groups will give us a test where we reject the null hypothesis. So that's why we look at this F critical value. So if our F value is greater than our F critical value, we would reject the null. So that's the first step. What we want.
You can't just look at a p-value and say 0.05.
Well, that's, yeah, but he wants to know what sum of squares would be about.
Right.
Okay. I mean, we could, but it's a little bit. This way is easier. Okay. We're going to do it. Some of you can do it within GoalSeek within Excel, but we're going to do it by hand. I think that's the easier way to learn it. Because I mean, ask each other about GoalSeek. So, the formulas here is sum of squares, our degrees of freedom, which is going to be fixed for this. Our mean square is equal to our sum of squares divided by our degrees of freedom. And our F is equal to our mean squares between groups divided by our mean squares within groups. And our F critical values will remain the same at 3.28. So we want our F to be equal to 3.28.
3.24.
3.24.
24. So the first thing we need to know, if RF is equal to 3.24, what is our F equal to? RF is equal to our mean squares between groups divided by our mean squares within groups are going to remain the same because our sum of squares within groups is going to remain the same, divided by 43.25. So if we multiply this whole equation by 43.25, our mean squares between groups must equal to 3.24 times 43.25. 140? Or 13? 140. 140.13. Let's leave it here. It's close enough. So this is what we need our mean squares between groups to be equal to in order to have an F value that's equal to our critical value. So what we're trying to find is not our mean squares, but our sum of squares. And we know that our mean squares is equal to our sum of squares divided by our degrees of freedom. So we know that 140 is going to be equal to our sum of squares between groups divided by our degrees of freedom, which is 3. We're going to multiply this whole equation by 3. So our sum of squares between groups, 420.4-ish, about. So we're saying that in order to have this test reject the null, to have a successful test for reject the null hypothesis, our sum of squares between groups has to be equal to 420.4. So do it out to more decimal places. I'm not going to because I'm not getting graded on my thing. But do we all get the gist on that? This is going to be important. We're going to get to the next tab and you'll get more practice on it. But this page 577 and looking at these ANOVA tables, he kind of likes to give you guys blank ANOVA tables and have you guys solve out. So, speaking of, here we go. We got a Blankonomic table. The sum of squares for treatment plus the sum of squares for air is going to equal our sum of squares for total. So the first one is just simply our sum of squares of air is going to equal our sum of squares total less our sum of squares for treatment. The next part, we have to figure out what our degrees of freedom is. Degrees of freedom is. In order to figure out what our degrees of freedom is, we have to figure out our N and our K. So N is going to be sample, total sample count. Sample. And K is our number of divisions in the sample, or so for this sample, it says we have a 5-factor test with 7 observations in each factor. The number of divisions, we have 5 factors in this test. So our K is going to be 5. Our N is going to be our number of factors times our number of observations. So we have in total 35 observations. So if we look down at our table, the treatment degrees of freedom is going to be equal to our number of factors minus 1. Our air degrees of freedom is going to be equal to our total sample size minus our number of factors, which is 5. And then our total degrees of freedom is going to be the addition between those two. So mean squares are going to be equal to our sum of squares divided by our degrees of freedom and our F value is going to be equal to our mean squares of our treatment divided by our mean squares of our air group. And our p-value is going to be equal to F dot distribution of a right tail. So our F value is going to be our X, and then degrees of freedom 1, degrees of freedom 2. P-value is there. So F dot distribution of right tail. For these ANOVA tests, they're always going to be right tail tests. And this right here will be a template that will come in handy probably on your final exam, I would imagine. Questions?
Is there in the book like it has all the formulas and stuff?
This slide.
Yep, page 577.
That's the
Yep. And so remember that really the most confusing formula on this one is going to be this F dot distribution of right tail. So just remember that one, but then the rest is just, these are all summations of each other. This is all dependent on how many factors we have, what our total population is. Mean square is just a sum of squares divided by our degrees of freedom. F is just the division of our two sum of squares, mean squares. Okay, a researcher asked 150 women and 170 men if they trust the federal government in preserving Social Security benefits. 89 women and 81 men responded yes. So, the first question says, what is the point estimate for the proportion of women who trust the federal government in preserving Social Security? So this one's pretty easy. 89 women trust the federal government in preserving Social Security out of 150 women. So our point estimate for the population is that 59% of women trust the federal government to preserve Social Security benefits. The next one says, do these measures of trust differ by gender? So, do these measures of trust differ by gender? We're running a hypothesis test with our null being that the population proportion, the proportion for the sample of women is equal to men. An alternative being that the proportion for women is not equal to the proportion for men. So we're doing proportions. It's chapter 11. In your fancy final exam review that I sent you, we can go to chapter 11.1. And here we have interval estimation of difference in population proportions and hypothesis testing difference between population proportions. And these are pretty much the same. We're running a two-tailed test. So we are not doing an interval estimation, we're doing a hypothesis test. If they wanted us to know between which two values is the difference, then we run an interval estimation. That gives us a confidence interval. This one's going to give us a hypothesis test. Copy this over to here, paste it in.
Hey Matt, on that first question, is there a reason why he gets all wordy and says point estimate of the proportion? Why did he just ask the proportion? Was it point?
So technically, here's why. The actual proportion is if we knew if we asked every woman in all of America whether or not they trusted the federal government to preserve Social Security, that would be the true proportion of women who trust Social Security. So we didn't do that. We took a sample of women, and so we have a point estimate of the proportion. That's just the word.
Or a sample proportion.
It's a sample, yeah. A sample proportion is a point estimate proportion.
Okay.
Yeah.
Thanks. That's why I was wondering.
Point estimate, just when we have sample values, we talk about point estimates. We're just talking about using that value from the sample as a point estimate.
Okay.
So if we take a sample of everyone's income, and I want to know what's the point estimate of everyone's income in this room, it's just going to be whatever the average income is in this sample.
$350,000.
Dollars. It was $350,000. I bring it down slightly. So, do these measures of trust differ by gender? So, here's where we have to. This template is good if we just give values, or it's good if we're given data. So it can work with data, or it can work with values. Today we're going to be working with just values, we're not giving data, so we can just type in these values. But if we're working with data, we'd have to highlight where the proper data exists. There's no data on this one, so we don't have to. So let's go here and we'll call this women. Call this men. Sample size. It's 150 women. For men, there was 170 men. Count response is the number of people who said yes. And the way this template works is if we had yes or no, we were trying to pick out yes or no from the data. This is a count if someone's answer is equal to yes. So for this, for us, yes for women was 89. Yes for men was 81. So we can see that 59% of women trust Social Security to be there when they retire, but only 48% of men trust Social Security to be there when they retire. So the rest of this will populate for us. Hypothesized value, we're saying 0, we're trying to test is a difference. So we're running a two-tailed test. So our p-value of our two-tailed test is 0.036. So 0.036 is less than our alpha value of 0.1. So 0.036 is less than our alpha value of 0.1. And we can say that there is a statistically significant difference in the amount of women who trust the federal government with Social Security and the amount of men who trust the government with Social Security. And p-value, we put that in there. So what we're saying is that since these two proportions are different, statistically different, and women's proportion is higher than men's, we can say that women have a higher trust in the federal government when it comes to Social Security than men. Questions?
Is it possible that you make the numbers a little bit bigger, Matt? Thank you.
And remember, this all comes from the template and when I sent you the final exam, chapter 11.1. Disappointment. And then find that at the end. Yeah, I've watched like 25 hours of this. I need to be close.
That's still 5-0?
Yeah. How hilarious was it the first game? We were here, and it took 2.5 hours. We didn't get to see it. And then every other game that I've watched, it's been 5 hours, and my girlfriend was very upset that so much baseball was on. And I wanted to tell you, those players is far more fun.
Oh, wait a second.
He's so quiet, right?
You haven't heard him, so.
Oh, I just heard it laugh. I was like, I thought you were laughing.
You got lights.
Yeah.
4 balls.
And I lose about as many balls in the dark as I do the lights. It's about the same. So any questions on this one? In chapter 11, we covered proportions. So tab G, I believe, is also from chapter 11. It is more proportions. Yay, proportions. So let's, first thing we're going to do, we're going to copy over the same one here. So I think we're going to use it. And then let's read through the question together. So, Minnesota had the highest turnout rate of any state in the 2012 presidential election. Political analysts wondered if turnout in rural Minnesota was higher than turnout in urban areas of the state. A sample shows that 663 of 884 registered voters in rural Minnesota voted in the 2012 presidential election, while 414 of 575 registered voters from urban Minnesota voted. Formulate a hypothesis that in the cells below that can be tested. So what does the question ask us? The question says, political analysts wondered if turnout in rural Minnesota was higher than turnout in urban Minnesota. So our hypothesis, since we are concerned about whether one is higher than the other, our hypothesis is going to be single-tailed. So if this is rural and this is urban, we're wondering if rural turnout is greater than urban turnout. So our alternative hypothesis is that rural turnout, the proportion of rural voters is greater than the proportion of urban voters. Man, these words are hard to say. And then our null is going to be that rural voters are less than or equal to urban voters. So how many rural?
Some peanut butter?
How many rural voters were there? There's 884 of them. How many urban voters were there? There's 575. How many turned out for the rural areas? 663. How many turned out for the urban areas? 414. Okay. Remember that rural is a word that's made for people who live in cities. To make people who live not in cities look stupid. So, what is the proportion sample of registered voters in rural Minnesota that voted in the 2012 election? 75% of our rural voters from our sample voted in the 2012 election. So, do the proportion of voters differ between urban and non-urban at an alpha value of 0.05? We're looking here, we did a one-tailed test. So we did a one-tailed test, which is a upper tail test. So if we look at our upper tail p-value, our upper tail p-value is 0.1014. So 0.1014 is greater than our alpha value of 0.05. So we would fail to reject the null. We cannot prove that rural voters turn out in greater numbers. So the proportion of voters differ. That's dumb too, the way that's written. Based on
Based on us accepting the null that
why is the language changing? No question. So we're going to accept the null. So let's just say, based on that, they do not differ. Or we cannot prove, based on our test results, we cannot prove that rural voters voted at a higher rate than urban voters. And then we could just say, if we ran a two-tailed test, that too would show us that there is no statistically significant difference between the two. P-value of our test is running a one-tailed test is this. The value of our test statistic is here. It's given to us in this template. And that, how we calculate a test statistic is the difference between the two means divided by our standard error. So questions on that one? It's pretty similar to when we run a t-test in means. It's only slightly different. Yep.
Is it wrong to just use like rural minus urban? No, sorry, I said rural. Minus urban is less than 0. Would that be wrong?
Less than or equal to 0.
Yep, you can do less than or equal to 0, yep, instead of either one. They're both the same. I like it this way for myself because it's easier for me to remember that. But that way, in case it gives you an actual value estimate for the difference, then that way is good too. They're both the same. Any other questions? Now we're into fun stuff. Chi-squared tests. The proportion. So when we use the ANOVA test allowed us to test the difference between more than just two means. So before we were just testing two means, and then we did the ANOVA, the F test, and then we test the difference between multiple means, more than two means. This is going to be a similar test. When we write this out, our null hypothesis is that proportion 1 is equal to proportion 2 is equal to proportion 3, and so on and so forth to proportion 9. And then our alternative hypothesis for all these tests is that H null does not hold. So this one says, Professor Smith grades homework at home, in the office, or at the student union. Her graduate assistant checks the homework for additional errors. That's funny. In the final score, reported the numbers of errors in the table below. So if we go here to the templates I sent you, 11.2, we have this template here where we have actual expected. So what we do here is, given this total population, we calculate our actual values, and then given how they're distributed out between the proportion of answers, we calculated what we truly expect those values to be if they're evenly distributed across all these three factors. And this is what they would be. And then we calculate our chi-squared value. Over.
You don't know values.
Okay, never mind. We'll just paste this in here. And then we have to take totals. these three, and I'm gonna take totals across. Once you take the totals all around and across, to populate for us. So our actual values here, if we had perfectly distributed across all three factors, this is what our expected values would be. And then our chi-squared test, we highlight our actual values and our expected values. Now for our actual values, we do not highlight our totals. We only highlight this 3x2 cell, depending on how many factors we have. Now, if we have 5 factors over yes or no, then we'd only highlight a 5x2 area box, and we would not highlight the totals. That's important. If we highlight the totals, we're not going to get a correct answer. We only want to highlight what's given to us. And then we highlight our calculated expected values based on those totals. And that's chi-square dot test. And that's going to populate us out a p-value. Things. So,
Chi-square dot IMV dot RT. Chi-square dot IMV dot RT.
oh yeah, to get your actual value. Degrees of freedom. Let me see. It's in the book somewhere.
You said it was
K. Degrees of freedom is k minus 1. So k is the number of factors. Here are number of factors. We have 3 factors. So 3 minus 1, our degrees of freedom is going to be 2. So our test statistic here. It was chi-squared dot inverse dot right tail. If we're given our p-value already, so we're given our probability area, and he wants to know our test statistic. So if we're given our area and we want to know our statistic, we always use our dot inverse equations.
and the degrees of freedom you have to. It's rows and columns.
They're not degrees of
It is.
freedom.
Three or 3 rows
Your
minus
columns
1.
minus 1 times your rows minus 1.
In this case, it is 2. but
Yeah,
you-
for
you have
3 by 2, it's just going to be factors minus 1.
Yeah.
Yeah, we have 2. Yeah, when we get bigger though, you guys are right.
Yeah.
The next question, we're going to need the rows minus 1 and column. So, the overall conclusion for this problem, I'll show you guys these formulas again. The overall conclusion for this problem, though, is that there is no difference between the proportions based on her home, office, or in the student union. So the teacher is equally accurate in the home office and student union. We find no difference between those 3 places in her grading abilities. No statistically significant difference, yeah.
So yes, so the error rate is the same.
But area is the same, yep. Is that the question?
Yeah.
Yes, professor has the same error rate. Mhm. So, tab I is similar to tab H, but instead of looking at proportion over 2 measures, we're now looking at proportion over 3 measures. So we have 3 measures and 3 factors here. So researcher recently evaluated the reputation of Arlo Industries and the quality of its management in a survey of 200 randomly selected employees. The results are summarized below. So management was either, the quality was either good, excellent, or fair, and the reputation is our factors. They can have a good, excellent reputation, a good reputation, or a fair reputation. Are the quality of managers and reputation scores above independent at alpha value of 0.5? So what we're trying to say is so is quality based on excellent reputation equal to the quality based on good reputation equal to the quality based on fair reputation, or is null does not hold? So there's reputation. We're essentially trying to answer, does the reputation of managers affect their actual job quality? So is reputation an accurate measure of the quality of managers doing their job? We can go to the template they sent you. So here you have a template for a 2 by 3, which is nice because that's what we did in the first question, is a 2 by 3. The second question, we had a template for what ended up being a 3 by 2. But this one isn't a 3 by 2. This one is a 3 by 3. So we can start having different proportions over more than 2 metrics, and we can have more than 2 or 3 factors. So if we go in this template document I sent you, there's a chi-square tab. So what I did in this chi-square tab is I made you a 10 by 10 chi-squared matrix. So in your test, when you have your final, you can pull this up, and I'm pretty sure he's not going to give you a bigger than a 10 by 10 chi-square matrix. So we can have up to 10 factors separating our populations, and we can have up to 10 different dividing proportions for our population.
And then just delete the rows you don't want.
You don't even have to delete the rows you don't want. This is set up so it'll just populate with it or populate without it. So how this works is we're going to go to our homework. We're going to take these values. We're going to copy them. We're going to paste them right here. So when we paste them in there, we get a 3 by 3 matrix in our actual values, and then we get a 3 by 3 matrix in our expected values. Everything else in the matrix populates with 0. We can ignore everything else. So for this test statistic, for a p-value, remember we do chi-squared test. We highlight our actual range, and we only highlight our actual range. And then we can highlight our expected range. Remember, only highlight your expected range. And we get a p-value here of 0.0019.
So if you highlighted the whole thing, it would give you something different.
Yeah, so we highlight the whole thing.
Because your degrees are.
Let's make it free. Yeah, it's gonna make your degrees of freedom all wonky. Bless you. So, are the quality of managers' reputations scores reported above independent? So, we're testing for this independence. We're going to reject this null hypothesis. So, if we reject that null hypothesis, that means that a manager's quality is not independent, is dependent upon the manager's reputation. So there's a dependency across the reputations, meaning that across all reputations, all qualities are not equal. Average quality is not equal. So let's just talk about what independent would be. If they were truly independent, if your reputation was independent from your quality score, we would have the same averages of, we'd have the same quality across all reputational managers. So we could have a manager that everybody loves, and then we have a manager that no one cares about, and then we have a manager everyone hates. And if we went and looked at how good they were managing their staff, all of their metrics would be equal to each other, the average of all their metrics. So instead, what we're saying is that there is codependence on how the quality of a manager is based on the reputation that manager gives. And we can look at the distribution of data and kind of see that there. So, are quality management and reputation scores independent? No, they are not independent. There is a statistical codependence between the reputation of a manager and the quality of that person's management. So the chi-squared, what is the chi-squared test statistic? We go back to our p-value. And our chi-squared test statistic is going to be equal to chi-squared right tail, this inverse of the right tail. This is our probability. And our degrees of freedom is going to be our factors minus 1. So our rows minus 1 times our columns minus 1. So we had 3 rows and 3 columns. So it's 2 times 2. Our degrees of freedom is 4. Our chi-squared test is 12.
It says 4 and 5.
Time to do that. Boom, 17. So, questions on this one?
How do we copy it to the other, or do you want to try to copy that?
Oh, if you want to copy this over, you would just do this.
You put fixed references in there.
Just copy it all. Go over your homework, and you can just paste that right here.
It doesn't like that.
No, it doesn't?
You put fixed cell references in there.
Okay. Well,
Oh,
let me see. Let me think about this.
Sit on the phone.
Here's how we can do it. Here's the best way to do it. Go to your homework tab. Add a new tab here. Call this tab work. Go to B2 where it sits in the original document. B3, copy from B3. Go back to your homework tab. Go to B3 and paste it in here into a new sheet. Or you can go through and you can unlock these cells, but I just did this because I created this myself. And you can do that.
Hey, Matt, can you show the equation for p-value?
Okay.
Thanks.
For p-value, and then test statistic. Test statistic is going to be chi-squared inverse right tail of this p-value, freedom, and the degrees of freedom from this one is 4 because you have 3 rows and 3 columns.
Okay.
And so degrees of freedom is rows minus 1.
Yeah.
Questions?
So now you said that the results are not independent and the p-value, since it's smaller than alpha, then the value is statistically significant, correct?
No, so the p-value is smaller than alpha, so independence would mean, if they were independent, that means the mean for each factor would be equal to one another. That would be our null hypothesis. So our null hypothesis is independence. Independence meaning your reputation does not affect the quality of your management skills. They're independent of each other. What we said was we rejected that null, and we said that your reputation does affect the quality of your management skills, effectively making them dependent on each other. So the question here says, are the scores reported above, are they independent? No, the scores are not independent because our p-value is less than our alpha value. So there's a statistically significant difference on the scores of managers based on their reputation. So independence means that your reputation would not affect your quality of management. So our null value here is independence. We just read it. This is independent. This is.
But you said that the value is statistically significant, correct?
There's no value to be statistically significant. The p-value is less than our alpha value, which means that the difference in the scores based on reputation, that's where the statistical significance is. So we're just testing whether or not scores, quality scores for given reputations are equal or they're not equal. And they're not equal, and since they're not equal, then the scores above are not independent because they're dependent on each other. And our p-value is less than our alpha value.
You like the tab H.
Yep.
Question there. On, the first question, that you have to assume an alpha value, right? Just to answer that.
Yep, for this one we have to assume an alpha value, we're just going to assume 0.05. And then when we look at our p-value, it's so high that really it
Doesn't matter.
we could assume 0.1 and it's still.
Okay, good.
Other questions on homework? What?
Like the only one where he didn't put it
Didn't
in.
specify. And always, if he doesn't specify, just remember 0.05 is what we roll with when he does not specify. Any questions on this or the midterm?
Can we go over the answer to the midterm?
It's always 27.
42.
42. I've read the book. Good book. Any other questions other than the exact answers to the midterm?
Don't think it was the exact answer, just
Okay.
statistically significant.
Yeah. People weren't here earlier. There's the one about the phone calls.
Yes.
I'm going to email him about that. This happened last year too. If I were doing it, I would set it up so that the alternative hypothesis is that mu is less than 15 minutes. Because if you set up the other way, you're kind of setting up with hopes that you fail to reject the null, which I never like to do. So I'll email him. I would say go either way, listen to your heart when it's calling you. And then I'll email him and make sure no one gets deducted on that.
Yeah, my heart and my logic are opposite. At least my logic, not my heart, my heart's not right.
Okay.
It's over. Skipping around. So that's why you're so happy.
and then it should be.
Oh, yeah.